Thank you very much, Dinesh. I'm glad and honored to speak here. I can tell you that the first wafer at 94 was nice, but wafer is getting better and better. So it's obviously some climax here. I'm going to talk about Minkowski sums. And before I even give you the layout of my talk, let me just define what Minkowski sums are. They were mentioned a couple of times already in this meeting. The definition is very simple. You're given two sets in Euclidean space, and you take every pair of sets, one from P and one from Q, and you sum them up as vectors. So here you have the case of 2 points, and it's the Minkowski sum is the vector sum. And here is a more complicated example. You have 2 polygons, and this is the Minkowski sum. You already see a slight potential problem with the computation. You start with simple polygons, and you get a more complex object, a polygon with holes. And these are named after the famous German mathematician Hermann Minkowski. So I'll start with a crash course on Minkowski sum in case you don't know, you don't have a lot of experience with them. Then I'll try to answer the question, should roboticists care about Minkowski sums? In order to compute Minkowski sums, you have to have efficient algorithm. I'll show you that these are fairly complex objects. And we have a certain gap in understanding the complexity of the construction of Minkowski sums, and I'll talk a little about it today. And actually, this gap guides the way we are trying to solve the problem in practice. And I'll mention some recent progress, both in theory and in practice, in computing Minkowski sum. I'll give you some challenges at the end. Now, since quite a few of you know what Minkowski sums are, I decided before I move on, something happened here, that before I move on to the mini course on Minkowski sums, I'll give you a small question so you won't be too bored during the introduction. And here's the question. I give you a nice set in the plane. It's not necessarily connected, but it's a nice set. And I look at the following sequence. The first element is the set itself. The second element is the sum of the sets with itself, but scaled down by 2. Then I take the sum, the Minkowski sum of the set with itself 3 times, scale it down by 3. And my question to you, and I'm asking not to shout it now if you see the solution, wait till the end of the mini course, where is this sequence heading? Let me give you a small hint. I'll just show you one set A, and here is a set A, not connected, even have a hole somewhere here. And I just want to show you the second, this is the first element of in the sequence, and this is the second element. So you have something to think about while I'm giving you some more information about Minkowski sums. Okay, if I give you 2 disks and I'm asking what's their sum, it's very simple. It's another disk whose radius is the sum of radii of the input disks. What about convex polytopes? Here at the bottom, you see a blue polytope, an orange polytope, and their Minkowski sum. This is also a fairly simple case. And the reason is that if you want to know what's the boundary point of the Minkowski sum in a certain direction, D in space, all you have to do is to go to the 2 summands and look for the farthest point in that direction in the 2 summands and sum these 2 vectors. And you get the appropriate point on the boundary of the convex polytope. You can use this fact to show that the sum of convex polytopes is a convex polytope. For convex polygons, if you have two polygons with m and n vertices, the sum has at most m plus n vertices. If you go to 3 dimension, the sum is slightly larger. It's m times n. We even know the exact number of vertices, but for now, just remember the theta mn. However, if you take arbitrary polyhedra, the object, the Minkowski sum, becomes much more complex. Remember, for two simple polygons, for two convex polygons, it has complexity m plus n in the plane. And if I give you two arbitrary polygons in a plane, the complexity jumps to m squared, n squared. And in 3-dimensional space, it's m cubed, n cubed, and these bounds are tight. You see an example here that you can get two polygons with m and n vertices, and the complexity of the Minkowski sum is actually m squared, n squared. Still, all these questions from combinatorial geometry point of view are trivial. You need to know very little in order to obtain these bounds, perhaps with the exception of the exact number of vertices in the 3-dimensional case. But there are curious questions in between. These are non-trivial. I give you one convex object and one non-convex object. For example, you see this cleaning robot in a cafe that has round chairs and round tables, and you use the standard idea of configuration space obstacles that I'll formally define soon, and you get an expansion of the green circles. The expanded circles now intersect. Suppose we have n green disks. If these were triangles, although you have n triangles to start with, if they are intersecting, the complexity of the free space or of the C obstacle is n squared. But because these are disks, you can show that the complexity is only linear in the number of disks. Again, it's a Minkowski sum of the green objects with the red object. The red object is convex, but the green object is not convex. And one of the nicest early results in computational geometry by Kedem, Livneh, Pach, and Sharir shows that this property extends from disks to other objects as long as every pair of regions, their boundaries intersect in at most 2 points. It appears in the first volume of the journal Discrete and Computational Geometry, a major journal in computational geometry. It took several years to extend this result to 3 dimensions. First, Chiap and I came up with a restricted result for a box moving a more arbitrary polyhedra. And then Aronov and Sharir gave a general bound for polyhedra. I don't give you the bounds because they have some parameters that need explanation, and I decided to skip it for now. Okay. How to represent Minkowski sums? If you only deal with convex objects, and mathematicians have studied Minkowski sum of convex polytopes in high dimensions, then you're only in the convex case. Topologically, it's rather simple to represent. But for most applications that I'm going to mention soon, the convex case is insufficient. And when you're going out of the convex case, look at the Minkowski sum of these two objects, you get a fairly something got stuck here. Sorry. I'll try to. You get a fairly complex object. You see, there is a boundary of the Minkowski sum here, which represents the fact that the star can slide in contact with these walls. There is a singular point here on the boundary of the Minkowski sum, which represents the fact that the star can be placed here, but it's immobilized here. And the suitable thing to represent this is something called arrangements of curves and surfaces, simply the subdivision of the plane of space by a collection of curves and surfaces into vertices, edges, faces, and higher dimensional cells. You see these nice pictures. They are not unrelated to the talk. They are actually related to arrangements, and I'll say more. They were generated by a program that uses arrangements, and I'll say more about them later. So the language that we use to represent Minkowski sums of arbitrary objects is the language of arrangements. Minkowski sums have many applications in robotics, automation, CAD/CAM, you name it. And here is a major reason why they are so useful. This simple claim. Two sets A and B intersect if and only if the Minkowski sum of A with minus B contains the origin. What is minus B? Is the set B reflected through the origin, or every coordinate in every point of the set B is negated. And this is the source of many useful applications. You probably know, here are Tomás Lozano Pérez's configuration space. It's a generalization of the earlier claim. I have a robot translating, I have obstacles. I take the Minkowski sum of the obstacles and a negated copy of the robot, and then if I have a free path for the reference point of the robot, then I have a free path for the robot, and it's exactly the same claim, only made dynamic. We have two general paradigms to compute Minkowski sum. One takes each sum and decomposes it into simpler objects. These are called the composition methods. The other methods ignore the interior of the summands and only look at their boundaries. They are called convolution methods, and I'll refer to each of them later. This is the end of my mini course, and does anybody know the answer to the question? Someone is willing to guess? Okay, let me show you something. Let me take another example that will give you an idea. Let's run this. This is the sequence. Yes, it converges to the convex hull of the set. And this is, in fact, well known for many years, for over 45 years. But this problem had a comeback recently when mathematicians asked the following question. Okay, it converges to the convex hull, but does the volume monotonically increase? And the surprising answer is the following. If you're in dimension 1, if you're on the real line, yes, the volume increases monotonically. If you're in dimension 12 or higher, this is no longer true. And if you're looking for an open problem, I decided not to present it yesterday, but what happens between dimension 2 and 11 is not known. Okay, so this is the end of the introduction to Minkowski sums. And let me address the question, should roboticists care about Minkowski sum? And if I'm standing here, this is because I think roboticists should know about Minkowski sums. And let me give you some reasons. So first of all, for translational motion planning, it gives you the ultimate answer. It's the ground truth. Here is a diamond robot. It translates in this apartment. You see the Minkowski sum on the other side, and it can tell you exactly how it can go from any point to any other free point. You have these extra dotted black lines. These are the vertical decomposition that makes it easy to plan the motion in the free space. Okay, but you tell me you prefer to solve the problem with sampling-based planar. That's perfectly fine. But here's a problem you'll probably find much more difficult to solve with sampling-based planars, and this is assembly planning. I give you a set of objects, I give you a product in its final state, and I ask you to plan the motion of the objects so that they form the final assembly. This is specifically the split star puzzle that appears at the end of some towers in an Escher drawing. And here, we use Minkowski sums on the way to solve this automatically. If I can make some historic remark here, at the beginning of the 90s, Wilson and Latom made a breakthrough in the study of assembly planning. They were at Stanford, and they observed that, contrary to what was known until that point, there are polynomial time algorithms to solve key problems in assembly planning. Polynomial in the number of parts in the assembly. Previously, only exponential time algorithms were known. But at the same lab, Lydia Kavaki and Jean-Claude Latom came up or made further moves with sampling-based planners. And as we know, sampling-based planners took over big time. I mean, many more problems that are tighter and are very difficult to cope with were put aside. I think it's good for all of us that sampling-based planners took over. I don't think that we would have been here have they not taken over. But I think the time is ripe to get back to those tighter, harder questions because there's new machinery to tackle them. Let me give you another example. It's a nice project that we were involved in recently. We were asked by a Japanese company to take a robotic cell with a conveyor belt and several packaging robots and squeeze the cell. They want to save real estate. So in the original settings, the robot's workspaces were disjoint. In the new setting, the robot's workspaces overlap. And now you have to react with collision detection and motion planning. And in order even to do collision detection fast, you really have to understand the geometry. It's difficult. It's very tight here. If you want more details, it appears in Case of last year. OK. Here is an experiment trying to mix sampling-based planning with exact geometric computing of Minkowski sums. It's part of Oren Zaltzman's PhD thesis. Here's the problem. It has 6 degrees of freedom. I have this C-shaped object, which we call Pac-Man, and a square. The green parts are the source position, and the red parts are the target position. So the square and the C-shape and the Pac-Man have to swap places. And the Pac-Man first have to swallow the square. And the experiment goes as follows. We take the square and progressively increase it. So it becomes a very tight problem. How do we attack it? We propose something that we call motion planning with manifold sampling. Instead of sampling just points, we sample whole subspaces, whole submanifolds. For example, I fix the orientation of the square and the Pac-Man, and I fix the position of the square, but I let the Pac-Man move around. This is a 2-dimensional problem, and I compute it exactly by using Minkowski sums. And what you see here is a comparison between manifold samples and PRM. And the x-axis is the tightness of the problem. And you see as the tightness goes up, at some point PRM breaks and MMS continues on. And surprisingly, although we are doing exact geometric computing with arbitrary precision number types, it doesn't pay too much. It doesn't take too much time to compute this, the exact submanifolds. It's true that this also breaks at some point because it's a sampling-based method, but it is a more powerful one, and we prove in what sense it can handle better narrow passages. I don't know, why is this stuck? Okay. Those of you with sharp eyes will see that this is from a scratch pad from the last ICRA, where Joe Vandenberg described a solution to smoothing a path for a self-driving car to me. And you get in the middle the original path. It's a polygonal path. And he applies Minkowski sums back and forth 3 times. And he gets, as a result, a nice path in the middle. Why not just smooth the corners? Because you have all sorts of boundary cases. And if you apply Minkowski sum on both sides, you get for free a very nice path at the end. I want to say that Minkowski sum can help you think of problems, even if you don't apply Minkowski sum. Think, for example, of minimum separation distance between 2 polyhedra, called penetration depth. It is very easily observed with Minkowski sums. It's the point on the boundary of the sum that is closest to the origin. Or another thought experiment. I guess many of you use collision detection packages from the group of Dinesh Manocha and Mingling. And let me talk a little about the bounding volume hierarchy using OBBs. One of the reasons that these packages work so effectively is that the OBB test for collision is super fast. They show that you only have to project them over 15 lines and check for overlap of segments on these lines. And if you want to see, they prove it in their own way, but if you want to see why only 15 lines, take 2 oriented bounding boxes, look at the Minkowski sum, or better yet, on the Gaussian map of the polytope of the Minkowski sum, and you immediately see where are these 15 directions. And it's easily generalizable to other special bounding volumes. Okay, when I gave the title of the talk, perhaps people don't know, but the basic motion planning problem was called piano movers, and the series of papers that John Kenny mentioned yesterday by Schwartz and Sharir is called On the Piano Movers Problem. But I also have piano printers in my title, and when I gave the titles, all the printed piano that I knew, I work a little in 3D printing, were toy pianos. Sure enough, last June, Steinway, the traditional maker of high-quality grand pianos, announced a new grand piano, you see it in the picture, with 3D printed components. How does this relate to Minkowski sums? In algorithms for 3D printing, Minkowski sums come up all the time. For tolerancing, as in other areas. For nesting, you may know the home printers that use dripping plastic, but manufacturing 3D printers, those that cost $1 million, use different techniques, typically based on powder that is sintered. And printing takes a lot of time and costs a lot of money. And you want to pack the printing volume as good as you can, with as many objects to be printed as you can. But you also have to obey rules of the printing, and you have to keep distances between the objects. And here Minkowski sums come to play. Another example is architects use 3D printing to scale down and print models. Now they take the building, they scale it down, and a column becomes like a thread that is unprintable. And you need to compensate for it. And an elegant way to compensate for it is to use Minkowski sums. And how does this relate to robotics? In many ways, people started printing robots. You see here robots from Daniela Russo's group, a toy robot that is sold, a new soft robot printed at Harvard. And the other direction also applies. There are robots that 3D print. This is a Dutch project where 2 robots are printing a steel bridge. They have a lot of nice pictures. I don't know if this is only PR or this is actually happening. At least conceptually, it's very, very nice. OK. So there are many reasons to have Minkowski sums in your toolbox. And now I want to talk a little about the actual computation of Minkowski sum and to tell you that we have a problem. Let's look at the simplest and safest algorithm for computing Minkowski sums of polyhedra. Decompose the polyhedra into convex subparts. Now, take every subpart of P with a subpart of Q. These are now convex. Therefore, computing their Minkowski sum is very easy. And at the end, you have to construct the union of all these subsums. Let's make it even more concrete. I give you 2 simple polygons, P and Q, with m plus 2 and n plus 2 vertices. I decompose P and Q into m and n triangles. I take a pair of triangles, it's a hexagon. I decompose the hexagon into 4 triangles. And now I have to construct the union of 4 mn triangles. Now, I mentioned earlier that if I have x triangle, the complexity of the union is x squared. So it might be m squared, n squared complexity. And I also showed you that Minkowski sum can have m squared, n squared complexity. This is very high. And Minkowski sum can have a large range. It can be 2 orders of magnitude. The result in some cases can be 2 orders of magnitude even for arbitrary polyhedra, and 3 orders of magnitude if they are convex. So we know how to compute it in the worst case, in time m squared, n squared. But I'd rather have an output-sensitive algorithm. It will work hard on hard problems where the Minkowski sum is very complex, and it will make less work if the Minkowski sum is sparse. And or take another question, which is more of a decision question. Does the Minkowski sum has holes? If it doesn't have holes, we can compute it very efficiently. Actually, this is a result that I have with Jack Snowing, who is sitting here from many years ago, that if it doesn't have holes, the complexity is very, very small. However, it seems to be difficult to have an output-sensitive algorithm for computing the union of triangles. Look at this very innocent, naive question. I give you a set of n integers, and I ask you if any 3 of them sum up to 0. It's trivial to solve it in n squared log n time. It's not so difficult to solve it in n squared time. About 20 years ago, Mark Overmars, who was in the first wafer and who organized wafers, wrote a paper with a master student where they observed that many geometric problems can be reduced to the 3-sum hard problem and be shown to the 3-sum problem and show that they are harder than 3-sum. And one of them was computing the set of triangles, or saying whether the set of triangles, the union of a set of triangles has holes, a hole in it. Now, we need to compute the union of 4 MN triangles. So it may sound as if we are in good company, and we will need m squared, n squared time by this discussion. However, our triangles are special. These are not arbitrary MN triangles. They are like a Cartesian product of M triangles and N triangles. So in fact, the mystery, we even don't know, we don't have an output-sensitive algorithm for computing the Minkowski sum, and we even don't know if it belongs to this family. It sounds as if it belongs to this family, but there's no proof of it. Let me just update you on one thing. There's a lot of action in computer science now on this type of problems. More key problems were identified. The title is Hardness in P, or Hardness of Easy Problems. And there was a breakthrough by Grönlund and Petty. They showed that free sum can be solved in subquadratic time. It's very little subquadratic. It's n squared over log n, but it's a major breakthrough. This said, there is no similar result for the union of triangle. It's still harder, but we don't know that now we can compute the union of triangles in n squared over log n time. The lower bound for the union of triangles remains n squared. Okay. All this mystery somehow guides the way we plan efficient algorithms for computing Minkowski sums. So we take a somewhat more efficient approach than the decomposition approach, and it's called the convolution approach. What is the convolution? Let me define it. It was suggested by Gibas, Ramshaw, and Stolfi many years ago. You take the Minkowski sum. By the way, I denote it with this x in a circle. This is the convolution. It refers only to the boundary, not to the actual volume of the sums. And what it tells you is which vertices of one polygon to take the sum of with the vertices of the other polygon. And here you see the convolution of this blue polygon and a brown polygon. You get this strange object. And what we know is that the boundary of the sum is included in the convolution of the boundaries. This is, in effect, a very easy fact to show. What do? We track the boundaries simultaneously to create a two-dimensional arrangement of curves, like here. We compute the winding numbers of faces in the arrangement. Don't worry if you don't know what winding numbers are. You have an example here. And you take the union of faces with positive winding numbers, and this is the Minkowski sum. This is rather difficult to do. So people suggested, let's not take the full convolution. The full convolution may have too many edges. Let's try to throw away some edges. And there is a well-known observation, again, from over 25 years ago, that you do not need to involve reflex vertices of the original summands in the sum. However, what happens here, if you throw away edges, you lose the nice cycle and the winding number properties. So Behar and Lien said, don't worry. We will find other ways to tell you which faces belong to the sum and which faces do not belong to the sum. And it's an effective filter to construct Minkowski sum using the convolution method. Recently, and this is what I want to tell you now as news, we came up with another global filter. You see here two polygons with holes, and the holes constitute a problem, because in the convolution method, I'm looking for boundaries, and now I have many more boundaries. The boundaries of the holes are all boundaries of the object, and I need to take care of them. And I'm trying to get rid of irrelevant holes. And the question is, are there irrelevant holes here? Or let's look at the simpler example. You have these two polygons, one has 3 holes and one has 2 holes. And I tell you that you can get rid of some of the holes. Not of all of them. There is still a hole. There are still holes that will show up in the final sum, but you can get rid of some of them. And what we have recently shown is that you can always get rid of all the holes of at least one polytope. And this turns out to be an effective filter. So the actual underlying theorem is that I have a hole in a polyhedron, and I denote by p hat the polyhedron with this whole field. Then the original Minkowski sum of p and q and the Minkowski sum of p hat and q are the same if and only if q doesn't fit under any translation in minus h, in a reflected copy of h around the origin. And this theorem says that you can kick out this hole, and both holes of the smaller polygon. And with some little more work, you can show that you can always fill in the holes of at least one polyhedron and still get the same Minkowski sum. And now you can answer this question: which holes can I fill in here? All of them. And now the computation becomes very easy. We have some other observations there. They are more subtle, and they are also exploited in the way we compute Minkowski sums. There is a lot of action about holes in Minkowski sums. It's very interesting. This is a result by a Russian mathematician who says his idea was the following. If I give you two convex polygons, their sum is convex, it doesn't have holes. Can I tweak a little the convexity? Can I push the edges in and out a little and still get an object without holes? And he gives a beautiful theorem. What can you do to the boundaries of the hole and of the polygons and still get a Minkowski sum without holes? It's a beautiful result. Okay, I want to talk a little about the practice of computing Minkowski sum and tell you about some progress we have along this line as well. And I want to mention this. I know that many people feel this if they are practitioners in various fields. I always feel that it's the most pronounced in computational geometry, but you may feel this about your own field. The gap between theory and practice is huge. And you may think that computing the sums is easy, but let me tell you, it is not. You have to worry about many, many things. You have to worry about the generacies, and you have to make careful work around the generacies. And all in all, it's a very big task and a difficult task. We addressed it. We addressed it as part of the larger Seagull projects. I want to slightly advertise the Seagull project. It started 20 years ago with the goal of making computational geometry algorithms applicable in practice. You have some numbers here. It's pretty well used. The kickoff meeting was in September 1996 in Zurich. We got back to Zurich this September, 3 months ago, to the same place to celebrate 20 years. They even took us to the Alps where they served this cake. And I was really impressed that the Swiss are so well organized that the coach of the train that took us to the Alps had Seagull sign on it, so we know where to go to. Minkowski sums are part of Seagull. They were developed by my group. They rely on the arrangement package, which was also developed at my lab. Just that you get an idea, the arrangement package is 100,000 lines of C++ code. It's intensively used in academia and also in some companies, also some big names here in the Bay Area. They don't like that we mention their names as user of the package. But I think it's sound and safe to use it. It works well with the Boolean set operation. It's robust and efficient. It supports Minkowski sum of two polygons by decomposition or convolution, and it also supports Minkowski sums with a disk, which is the offset operation. These are the key players, students of mine, who contributed to the Minkowski sum package. We have a book with Effie Fogel and Ron Vine that gives a detailed description of what's behind each step of the package and how to use it. I spoke so far on two-dimensional Minkowski sums. We also do Minkowski sums of polytopes. The way we do it, we take the Gaussian map of the two polytopes and we overlay them of the sphere, and we compute the overlay on the sphere, and this gives you the Minkowski sum of the two polytopes. If you have tried to write code on a sphere, you may appreciate that it's not so trivial. So here you see an enlargement of the Gaussian map of the overlay of the Gaussian maps of the two polytopes. Okay, let me talk a little about problems and challenges. This is, in fact, a very sad, dirty laundry slide, because there's not really a complete, exact Minkowski sum solution in practice. It's very difficult. There are some approximate solutions by Lien et al. And from Dinesh Manocha, but there's not the analog of the two-dimensional Minkowski sum. We don't have it in 3 dimensions. Peter Hachenberger came up with a solution. It's still very, very slow and not totally robust, at least as I hear. One of the problems is that we don't have a complete solution to the 3-dimensional software problem. There are many issues on the way. I want to mention the generacies. These are very hard. And of course, what I'm looking here is for an exact solution. And you may wonder, what is this obsession with exactness? Why do I need an exact solution? No engineering problems need absolute precision. However, we mainly use exactness as a way to guarantee the correctness of the results and the result being consistent. It's a structure that has both topology and numerical values, and the only general way in 3 dimensions that we know to achieve a consistent structure is through exact computation. I don't mind rounding the vertices and getting, I don't need 17.005 for a coordinate. I would settle for something rounded. But even rounding, in which we are very good in 2 dimensions, we simply don't know what to do in 3 dimensions. There is not a general, correct, efficient rounding methods for even polyhedral structures in 3-dimensional space. Let me mention a few more problems. I mentioned MMS, the motion planning with manifold samples that helps you deal with tighter questions. If we will have 3-dimensional Minkowski sums, we could push it higher in the dimension. I should tell you that MMS comes with full probabilistic completeness guarantees. I told you that I don't know how to compute output-sensitive Minkowski sums. There are some tricks around it. They are a little dirty, and they are called quasi-output-sensitive. You invent additional parameters that come up during the algorithm, and probably this is a line where we can do something. I gave you a filter where I eliminate holes. What did I do? I took the input summons and I changed one of them to make it simpler. I changed it by filling in holes. Perhaps I could do further changes to further reduce the complexity of the computation of the Minkowski sum. Okay. don't worry, these are not theorems just before I finish my talk. These are take-home messages. One is that Minkowski sums can assist in solving currently unsolvable fine a tight motion planning problems. Then you don't have to develop them yourself. They are ready-made solutions. They are open source. They are available to everybody. And you don't need to give up sampling-based methods. They are wonderful. Fuse them with the exact arrangements and Minkowski sums. Many, many people helped me. I don't mention even all of them here. There are many dear collaborators that I have in the audience. I apologize for the names that I have omitted. Many people worked on the arrangements and Minkowski sum package. I want to explain the nicer picture that you saw throughout. There's an American artist, Jeb Geither. He wrote a program that generates pictures, and he uses Siegel arrangements. And I encourage you to go to his Facebook page to read about his experience with Siegel arrangements. He's soon going to publish a post where he explains how his software produces these pictures. Thank you.
Thank you, Danny. Not only gave a great talk, but he finished in time. So we have time for a few questions. Yes, your microphone.
So great talk. There's a way to describe benign non-convexity in the language of SOS convexity, sum of squares. Has anybody looked into how Minkowski sums behave under the regime of benign non-convexity?
I would be interested to know about, I don't know this specific one, but I think that the only place where people looked at near convexity is the work by Roman Karasev. He mentions other measures, but I think he was the first one to use it for Minkowski sums. There are many more theorems about special cases, but using convexity, I'm only aware of Roman Karasev.
Thanks for the talk. Is this on? Yeah, that was a great talk. Thanks. I'm wondering, you were talking about the decomposition method, the union of triangles being the really challenging part. And I'm just wondering in practice, when is that an important problem to actually solve? So for collision checking, for example, I can just collision check against a set of triangles or other shapes instead of actually computing the full closed form set. So is that I guess in practice, when do you actually need to solve that?
I argue that there are many problems that you need the exact description of the C-space obstacles, in particular in assembly planning. And this is somewhat orthogonal to the union of the triangles. The union of triangles is a technical problem how to speed up. But my premise in arguing that we should use Minkowski sums, that there are some problems where just collision detection, where you discretely check if a configuration is free or not, may not be sufficient in certain problems, such as in assembly planning. I hope I answered your question.
Yeah, thanks. I guess a small follow-up would be, would you still recommend trying to use something other than decomposition if you don't care about the union of computing the exact union at the end, or is decomposition just fine and I should keep using it?
Yes. So there's work by Dinesh, there's work by Jiming Lian. There are alternatives. If you are not worried about the exact object, there are alternatives.
Thanks.
More questions?
Thanks, Dan, for the wonderful talk. So Leslie last night called machine learning the elephant in the room, and the elephant is going to enter in the room the next session. So for some of the talks about the importance of exact computation, what do you see the relationship with machine learning is, for geometric problems and challenges?
It's too difficult a question, not politically, technically. I really believe that there are problems where you will need to understand the geometry. Perhaps in 10 years, deep nets or deep learning will be able to solve assembly planning in tight quarters. I don't see the roadmap to there. I think there are still problems where we really need to understand the geometry. Perhaps I'm just convincing myself that my hammer is useful, but I don't see the roadmap how you overcome understanding the geometry. I had an interesting talk with a guy who's working in machine learning in the context of assembly planning. It's true, you may want machine learning to take the parts and put them together. It's a complex procedure where learning can help you locally. But at first, you would like someone to give you the general plan. So I do see some coexistence between the two at the final stand, and learning coming to the final stage where you put things together. But the general plan, how to go there, how to take subparts, I don't see, I think you will still need more traditional methods.
Ken.
Danny, thank you. There's so many interesting ideas you raised here, and I want to ask you a bit more about this quasi-convexity, because in the context of assemblies, as you're discussing, it seems as though you have some control over the shapes. I mean, as a designer, you could modify the shapes slightly. So I'm asking about, has work been done on the idea of how can you minimally modify shapes to achieve the quasi-convexity properties?
Okay, there is work by Chris Hauser on moving things in an assembly a little apart. I think that there's a lot of new coming work in 3D printing, how to modify slightly to make it more suitable for 3D printing. These are, in principle, very difficult questions because they seem open-ended. You can do everything. Again, as I say, the understanding of quasi-convexity, I think, is pretty limited in terms of its usage. I think a wonderful starting point is the Karasev paper. He cites 5 other papers on, and actually, the traditional result that the riddle that I gave you in the beginning, it was actually resolved by economists, I think. And they also discuss a little bit how close you get to convexity. It's fascinating. I don't have anything. I think these are very difficult problems. I think they are interesting, but I don't have any advice to give you besides looking at these references.
Time for one last quick question before we go for the break. Okay, if not, thank you very much, Danny, for a great talk. And